Hello, my name is Scott. I wanted to address a couple problems that I cut from website. I didn't mention them in class, but now the head honcho is talking about putting them back into the test. So I'm going ahead and cover them very quickly. And these are exponential and log limit problems. So we're going to do basically two examples. And the key to all of these problems is the following. All right, so there's this property of continuity that says the following. So let's let g of x, this is not really a theorem, it's just a property of continuity, so we'll just say theorem. So let's let f and g be functions. And then if f is continuous, a in R, now, if f is continuous, and if the limit as x goes to a, we'll just say from the left of g of x equals L. In other words, the limit exists. Then then the limit as x goes to a from the left of f of g of x equals f of L. So in other words, the limit as x goes to a from the left of f of x, f of g of x, equals the limit equals f of the limit as x goes to a from the left of g of x. Okay, so there's this idea that I can pass the limit sign through continuous functions. So the way you do all of these problems, okay, and it's essential to note that log and exponential, the exp to the x, or the exponential function, right? So we'll just do that as a separate thing. Exp and ln are both continuous on their domains. So that means no matter what I've got, I can just pass through I can just pass through the limit sign if I get something that's a composition of ln and something else. So to do some examples, there are a couple of these in your book. Let's just talk about a few of these. So here's one from, oops, that's the wrong section. So here is one from this is number 30 from section 3.1. And it says the following. It wants, so examples. This is section 3.1, number 30. Okay, so what I'm going to do, the question is as follows. The limit as x goes to pi over 2 from the right of e to the tan of x. Now, there are a couple strategies for this. I can kind of just say y and then do the limit and then I do, but let's just look at this. The whole idea here, because e to the x is continuous, I just kind of pass it through. So I go, that's the same thing as e, and I should write exp because it's easier if you're dealing with these limit things, but I'll just do it with this. The limit as x goes to pi over 2 from the right of tan of x. So let's look at the limit as x goes to pi over 2 from the right of tan of x. So the limit as x goes to pi over 2 from the right of tan, it's the same thing as sine over cosine. Goes to pi over 2 from the right of sine of x over cosine. Now, as I go to pi over 2 from the right, cosine is going to be the problem, right? Because sine is just going to 1. I mean, it's going, to the right. So technically it's going to 1 plus, but who cares, right? Cosine here, however, is going to, if you look at either the graph of the cosine or the unit circle, if you look at the unit circle here, cosine is going to be, the eastiness is going to 0, but it's going to 0 from the negative direction, right? It's going like this, and I'm going to 0 from a negative direction. So I'm just going to say that this is 0 minus. And 1 over 0 minus is negative infinity. Now, I'm going to get yelled at, you can't just do that. You can't just say e to the negative infinity. I'm going to go ahead and say I can say it. So I wind up with this thing, e to the negative infinity. Well, as e to the x, as e gets really negative, e to the x gets closer and closer to 0. So this is going to be 0. And that's how you do these kinds of problems. You just kind of throw them in there, figure out what's going on, and then go with it. So the fact is, you need just these couple of facts. You need these kinds of thoughts in your head here when you do them, right? You need to know what the limits are of e to the x. It looks like this. So e to the x, e to the infinity is infinity, and e to the negative infinity equals 0. And then you kind of need the log ones. And the log, since they're inverses, you actually only have to remember one of them because you just flip it over the line f of x equals x, or y equals x. You flip it across that line there, and you get the inverse. So log of 0 plus. Notice log is not defined in any negative or at 0. But log of 0 plus is negative infinity. And log of infinity equals infinity. So if you kind of just remember those, and sure, I'm going to get yelled at because, oh, you can't remember that. You don't really have infinity, right? And 0 plus isn't really a number. Well, it's an infinitesimal and an infinite. Okay, it's just, you can define them properly and prove all these things as theorems, and that's all well and good. And I don't want to, yell at people who love to do that kind of stuff, but for our purposes, good enough for government work. All right, so let's do another one of these. Let's do one of these for log. So let's do, this is number 73. So 73 from section 3.2, not 3.3. And it is the limit as x goes to 0 of ln of cosine of x. Oh, and by the way, up here, this applies for, and it works for, I should just say, and it works for x to a plus and x to a. So, you know, I did it for the left-hand side, but it holds for the right-hand side, and it holds for the two-handed limits as well. All right, so let's look at this one here. Well, first of all, the law, if this thing goes to 0, I'm actually in, if log of cosine of x, if cosine of x went to 0, as x went to 0, it'd actually be in trouble because the log of 0 is not defined, and there's no limit to from the left. It's just not defined. But it's this cosine bit in here. So let's see what happens here. So since ln is continuous, I could just kind of go ln of limit as x goes to 0 of cosine of x. Now, cosine is also a continuous function. It didn't need to be. All that had to happen was the limit here. But cosine, if I throw my little unit circle over here, my eastiness at 0 is 1 in both directions. So this is going to equal the natural log of 1. Now, which of course begs the question, what is the natural log of 1? Well, the log of anything, okay, the log with any positive or any base greater than 1 of 1 is 0. And you can see that because remember what log asks. ln of x asks the question, for what y does e to the y equals 0? Right? That's its whole purpose in life. It's an inverse. Right? Its whole purpose in life is the following. It's y equals ln of x. I take the exp of both sides. And I wind up with exp of y equals exp of ln of x. And the exp and ln are inverses, so they just equal, when I compose them, I just get x. So again, for what y, I'm sorry, this should be an x here. So for what y does e to the y equal x? So for what y does e to the y equal 1? And of course, that would mean y equals 0, because anything to the 0 power is 1. Now, quick thing, it doesn't matter. The bases don't really matter as long as they're all greater than 1. And I'm going to put that down here. All of these functions at the infinity look at the extremes look the same, except for, so all the bases c look the same if c is greater than 1 at the boundaries. So what I mean by that is, right, the limit as x goes to infinity of c to the x equals infinity for c greater than 1. I'm sorry, greater than 1. All right, so as long as my c is greater than 1, I don't care. And the limit as x goes to infinity of c to the, I'm sorry, as x goes to negative infinity of c to the x equals 0. for c greater than 1. The limit as x goes to infinity of log base c of x equals infinity for c greater than infinity. I'm sorry, for c greater than 1. And the limit as x goes to 0 from the right of log base c of x equals negative infinity for c greater than 1. In other words, they all act the same as the natural exponent and the natural log. As long at the extremes. Obviously, the stuff in the middle's going to be different. But at the ends, right? At infinity and at negative infinity for c to the x, and at infinity and 0 plus for log of any base that's greater than 1, they all look the same. Okay? All right, so that's how you do those problems.